Phase motors. We have a lot of stuff to get through in a lot amount of time. Not a lot of time. So it's my intention. Normally I drill in a little deeper on these PowerPoints that the book puts out to broaden your horizons a little bit to what actually is going on outside of what the book has for you. But in this particular, especially today and then moving forward, we have the one that the book has is decent, and then there's several other ones that the same guy that wrote the book has given us. And the other ones, the supplemental ones for single phase motors, are awesome. They have really awesome graphics that kind of illustrate exactly how the operation of these motors work. So it's my kind of intention not to spend a lot of time with discussion and just drill through this first one especially, and then get into the actual cool PDFs that actually have some valuable information and some good graphics. So today we're kind of going to just try to fly through this first one. If we get through the first one, I have intentions of starting up the second ones and just getting as much out of the way in the lecture part of this as we can, so we can start moving into the lab with a little bit more background on what we're doing. So without that, I'm going to get set up here to get started. Anybody have any questions on the test? Well, I do have intentions on going over it, or maybe not necessarily going over it, but I thought I would just give you guys an answer sheet where you could go through and look at what you got done, and that way you have the right answers, because I don't really want to waste time in class going through that. There's still a few people that need to go through it the second round, although that was over 3 weeks ago that we took that test. So with that said, let's get it on. Okay, gentlemen. For those of you who pay attention to me on our MyWDT, you would have known that our Chapter 18 review questions were due today. I had them due Friday, but since we didn't have class Friday, I changed that to today. Still didn't get everybody's in there, so we can't really go over those. Those of you who didn't submit them today have until Friday to get them done. Every day past today will be a 10% deduction until Friday, and then I'm going to shut it down. So you can get them in tomorrow, you still get a 90% and so on. So moving forward, single phase motors. Okay, our objectives after studying this unit: you should be able to list the different types of split phase motors and discuss their operation, reverse the direction of rotation of a split phase motor, discuss the operation of multi-speed split phase motors, and discuss the operation of shaded pole and universal motors. Okay, well, I don't expect you to know that after today, but hopefully after the end of this little unit that we're going to have on single phase motors, you should be there. Okay, split phase, single phase and split phase motors. Many different types with different operating principles. Split phase motors, the types are resistance start, induction run, capacitor start, induction run, capacitor start, capacitor run, or permanent split capacitor. That's the more common name, is PSC on those. And they operate on the principle of a rotating magnetic field, but field cannot be produced with only one phase. Okay, this is what we need to start understanding about where we're moving here. So the two-phase system produced when using an alternator with two sets of coils wound 90 degrees apart. The voltages are 90 degrees out of phase. So that's pretty much what we're going to have on a standard residential transformer. Is going to have two phases 90 degrees apart that are going to be wound to where when we add them together we get 240, and when we cut them in half we get 120. It's pretty standard. All right. Stator windings. Start winding is small wire near the top of the stator core, and we will actually have some more good illustrations of these when we get past this initial PowerPoint here. The run winding are large wires in the bottom of the stator core. Apply power to the stator, current flows through both windings, but lags in the run winding, creating the field. So when we talk about start and run windings, the difference in where they are in the stator are going to be how we get the phase shift in order to create that rotational field. Okay. All right. Here we got the picture of a alternator. Two-phase alternator produces voltages that are 90 degrees out of phase with each other. The start and run windings are connected in parallel with each other. So we can see down here, here's the phase relationship of a single phase system, 90 degrees apart. Here we can see that phase relationship down here. Here's the phases. We apply voltages up here. So the starting current and the running current are naturally going to shift because of where they are in the line. Okay. Now, that whole theory kind of becomes a little bit more evident when we add a capacitor in there instead of using that phase shift there. We start to use the capacitors phase shift that stuff. And we have to figure in the phase shift with the current as well as the voltage. It is my intention to kind of spend a little bit more time on each one of these different type of motors as we move through this. So please just start to be aware of what they are and pick up the high points here, the bulleted items. Resistance start induction run motors. Start winding is more resistive than the run and causes an out of phase condition. Okay, so when we have the two windings, they're both being energized at the same time, but one of them is more resistive, and which is going to cause the current to grow and the voltage to lag. So as we're having a higher resistance, the current's going to go up and the voltage is going to go down because they're inversely proportional. And that reaction from between the start windings and the run winding is what causes the phase shift. Okay, because like we said earlier, we can't have if we had just a single hump in there, it wouldn't start the rotation. Okay. The starting torque depends on the strength of the rotor/stator magnetic fields and phase angle differences between current and start and run windings. Okay, disconnect the start winding. Once the rotor reaches approximately 75% of the rated speed of the motor, will operate with only the run winding energized. Non-hermetically sealed, which means a motor that you can actually take apart and get into. Non-hermetically sealed motors use a centrifugal switch to disconnect the start winding. So I think the motor that we have with the piece cut out of it, we can definitely see the switch in there. And once we actually run these our new motors, and we get to run those, we'll be able to hear when it starts up. Should be able to hear a small click, but even more evident is when it slows back down. We'll hear that switch click back in. I promise you'll get to hear that. So, resistance start induction run motors continued. Starting hermetically sealed motors. So hermetically sealed motors are something that we would typically find. How many of you guys have built in the inside of your air conditioning unit? The compressor, the compressor in there, the little black thing on the bottom, that is a hermetically sealed single phase motor. That means that you can't open it up and look at it because it's all put together in one unit. Closed up. Okay, non-hermetically sealed, they're kind of like the motors that we have out in the lab. I can grab a compressor from next door and show you guys the difference if you want to see it. Just remember that hermetically sealed, just remember sealed means that you can't get in there and work on it or take it apart. Okay. Hermetically sealed rotors used externally mounted starting relay to disconnect the start windings. I'll show you guys a picture of that. The better slides. The hot wire relay uses a thermostat and rapidly heating wire to disconnect wires from the starting or overload, or they have a current relay that connects and disconnects the start winding according to current flow. Now, I have a couple of those we can look at too. The relationship of the stator and rotor fields. Power to the stator induces a voltage in the rotor. The magnetic attraction turns the rotor. Okay, so what that's saying is as we apply the voltage to the stator, the coils that are around the rotor that we're not physically connected to, that application of that voltage to that rotor is what's going to induce a voltage. Applying the voltage to the stator is going to induce a voltage into the rotor, and that is what's going to cause the rotation of the rotor. I'm talking a little fast because there's a lot of stuff to get through on this, and I want you guys to especially be able to see these other slides. Resistance start induction run motors continued. The relationship of stator and rotor fields. Motor rotation is determined by the direction of rotation of the magnetic field on startup. And you change the direction of one of these by reversing the connection of the start or the run winding, not both. So remember when we had DC motors and some of us changed both of the field and the armature leads and we got it to run the same damn way? Well, these are very similar to that. If you change both the start and the run winding, flip both of them, the motor will continue to run the way that it ran before. So you only have to change one, either the start or the run. Okay? That's how you change the rotation on these guys. And it'll become evident when we actually look at our new motors. They have really nice drawings on there to let us know. Okay, pretty much it on that. Now we're going to talk capacitor start induction run. All right, identical running characteristics to the resistance start motor, but different starting characteristics. AC electrolytic capacitor in series with a centrifugal switch in start winding, that's the difference, produces a significantly higher starting torque because start winding current leads applied voltage. Okay, so when we insert a capacitor, that action of that capacitive reactance, remember Scott talking about that, is actually going to phase shift the current of the applied voltage ahead of the applied voltage. Okay, that's what the capacitor does. And that reaction gives us a more evident and higher starting torque. And you'll surely be able to see those. Okay. Okay. Frequent starting can cause the capacitor to overheat. Yep. Use capacitors with the correct microfarad to ensure correct phase angle difference. All right. So if we ever get called to a job that we have to change out a capacitor, we can put one in there that has a bigger farad rating. You can go bigger, but you cannot go smaller. You'll blow that sucker up. Okay. Get an over voltage on that thing, and then it'll just go right in your hand. Hopefully not in your hand, but it could if you're hooked up to it. All right. So here we have the drawings of the electrolytic capacitor. It's connected in series with the start winding. There's that secret centrifugal switch in there that's going to drop that whole thing out whenever we get to 75%. And that's a great spot to throw in dual voltage windings for a split phase motor. Okay, I guess they just wanted to have you see that there. To talk about this, dual voltage split phase motors and direction of rotation. Many split phase motors are designed to operate on either 120 or 240 AC volts. 2 sets of run windings, 1 or 2 sets of start windings. There's the figure that we had, I think 18, nope, maybe the next one for low voltage operation. All right, we're gonna have to come back to it. Determining the direction of rotation for a split phase motor, face the rear of the motor and examine the terminal connections. So when you're determining the rotation of the motor, find that determination as you sit at the bell side, not the shaft side. Okay, on dual shaft motors, it's going to be clockwise one way, going to be counterclockwise the other way. You just have to look at it. But on single shaft rotors, you sit from the bell housing and you look toward the shaft. Okay, that's how you determine which direction it's rotating, either clockwise or counterclockwise. Okay, this is kind of the same principle as when you're in your car. Okay, the driver's side's on the left hand because you're sitting in there toward the rear, and the passenger side's on the right side, right? Yeah, sure. Okay. All right. Capacitor start, capacitor run motors. The start winding stays energized at all times. The capacitor connected in series supplies it with a constant leading current to the start winding. This operates on the principle of continuous rotating magnetic field in the stator. Two-phase motor Excellent starting and running torque, highly efficient, may use a second capacitor during starting to improve torque, and that will disconnect at 75% of full speed. So capacitor start, capacitor run, or permanent split capacitor, I think, PSC. That's what we have going on here. So just start to remember these terms because you'll start to really see them make sense once we get a little deeper in. Yes, sir.
With all these drawings like this, how familiar should we be with the way that these motors are, like schematic, etc.? Will it help us, or will it? Well, I mean, how much will it help us regarding?
So the test, I can't tell you because I haven't looked at it yet. But as far as knowing them for your job, they usually will be marked on the wiring terminations will be marked on the motor themselves, and that's mostly what you have to be concerned about. Okay.
So you should just know, like, okay, well, this is this.
Just remember that looking, this is a drawing showing you what the coils look like inside, but what you're going to see when you wire that is just going to be the wires, and the wires are going to, the nameplate will tell you how to wire the wires.
Okay. So determining the direction of rotation for a split phase motor. You can see there, the connections points here. If we're going to want to run this clockwise, we have our jumper from T1 to T5 on one phase and from T4 to T8 on the other. If we want to run counterclockwise, we jump that 4 to 5 and 1 to 8. Okay. And I'm not going to probably kill you guys on this because, like I said, all of the motor connections should be somewhere available on the nameplate. And if you can't find them on the nameplate, there's some information on there that you can get to that point and you can find out how to hook them up. Like an old motor, usually you can find a manufacturer name and on your phone download what the specs are for the motor. Most of the time you can do that. All right, so capacitor start, capacitor run motor there in the next figure. Nothing too crazy about that. Here we have the final picture on this stage is the potential relay connection. Not going to care too much about that at this point. All right, so shaded pole. Now we're actually going to talk about one of the most basic types of AC motor. These are fart fan motors, really small, just basic rotating magnetic field around a rotor. They're super simple. Shaded pole induction motors. Squirrel cage rotor has no start windings or centrifugal switch. Rotating magnetic field created by a shading coil wound around one end of each pole piece. And that is called the shading coil. And it acts like a transformer with shorted secondary windings, so a large amount of current flowing through the shading coil opposes the change of the magnetic flux. Now, I have some pretty cool stuff talking about this, but honestly, they're so simple. We can take one apart. They're so simple that it's like, why really spend a lot of time on them? Most of the time, if you have a shaded pole motor going to go bad, you're just going to throw the damn thing away and buy a new one. Like a fart fan, like $10. So they're really that simple. Another place that you'll find them that you may not be as familiar with them in, as opposed to a fart fan, is in the furnaces over next door. They're also called induction motors. Okay, so if you guys are doing work, get a little trouble call on your furnace, go in there and read out what the lights are telling you and follow out your circuit, find out that you have an induction motor bad. It's happened to me. I called up the heat guys and I said, hey, pretty sure I got an induction fan gone. You have the part? Yeah, we got the part. Come on over and plug it in and get you back going here. So just being aware of how these things work, is what it is. All right. So here's actually the outside piece. This guy right here is going to be the stator. And then obviously in here, does anybody know why they call it the squirrel cage rotor?
It's got like a little.
It's got a little, no?
well, I was trying to, I don't even know how to put it. It's like a fan, but instead of a bladed fan, it's little blades around a circle.
Yes, this is what they're trying to explain in this is 4 page. Essentially, what this is this could be, if you were to take the actual core of the rotor out, what they're meaning by squirrel cage is you can put a squirrel inside of this space and basically add a trap into it. Okay, so you have each one of these metal bars going through here is going to be continuous. That's what we're trying to say. There's several different types. I think we looked at a few in VC. I think we got some illustrations on VC where they'll either have just one circle or they'll have a long bar with a circle down here. This is the squirrel cage we were talking about with a shaded pole.
Okay. There's the schematic form. Very simple. Speed in an AC motor is determined by what? Frequency. That's what we use to control the speed. Determined by the same factors as the sync motor, frequency, and the number of stator poles. Okay, so if we were to take 2 of these poles out here and we only had a 2-pole shaded pole motor here, it would be slower. Okay, the reason why it's faster is because we don't have as far of a space for the magnetic poles to on the rotor to disintegrate, I guess you could call it, dissipate. All right, general operating characteristics are low starting and running torque. You can almost stop these things with your hand when they're plugged into 120 volts. If you had a fan blade on them, for sure you could stop them with your hand. Rotor turns in the direction that the rotating magnetic field moves across the pole face, and these are considered non-reversible, but they can be reversed by turning the stator winding around. But honestly, as long as your fan blades are pitched the right direction, you should never have to reverse one of these. I mean, this is just as simple as they are. They're used for fart fans. Don't try to change the direction of rotation in your fart fan, Travis. Don't do it. Because then you're going to be pushing the farts back on you. Can't do that, can we, Tanner? No, we don't want to do that. Multi-speed motors. Consequent pole single phase motors. Operate like a 3-phase consequent pole motor. Change speed by reversing the current through the alternating poles or changing the total number of stator poles. Multi-speed fan motors are usually wound with 2 to 5 steps of speed to obtain speed changes by inserting inductance in series with the run winding. How would you ever insert an inductance into something? Add a coil. Woo! Certain speed changes by inserting inductance into a series with a run winding. We just add an inductor into series with the run winding. Small ranges between speeds, high wire impedance used to operate low torque loads. There it is. 3-speed motor. You just basically change the speed by adding more inductance. Okay? Pretty simple. There's a Warren motor for your viewing pleasure. Single-phase sync motors operate on the principle of a rotating magnetic field developed by the shaded pole stator. Operate at a synchronous speed but do not require DC excitation. Warren motors, laminated stator core with 2 poles, single coil, steel laminations form crossbars of a rotor shaft, and a Holtz motor is a slotted rotor with 6 salient poles. A lot of the stuff right there we will be answering when we move forward, okay? Repulsion motors and the construction of repulsion motors. There are 3 types of operating traits: repulsion, repulsion start induction run, and repulsion induction motors. Construction of repulsion motors. Repulsion motors operate on the principle that like magnetic poles repel each other. Stator contains only a run winding and no start winding. Brushes and repulsion motors are shorted together to provide a current path through the parts of the armature. Okay. Construction of repulsion motors. I can tell you on this just side note here that there's not a lot of repulsion motors around. Okay. Not a heck of a lot of them. The operation, Induction motor does not operate on the principle of a rotating magnetic field. The stator field repels the armature field. Armature rotates. They contain the same number of brushes as stator poles. So the brush position, oh man, we have a brushed AC motor here. Maximum torque when brushes are 15 degrees on either side of the pole pieces, and repulsion motors have excellent start and running torque but unstable speed. Repulsion start, induction run motors start as a repulsion motor but runs as a squirrel cage motor. It has brush riding and brush lifting types. Brush riding motor uses axial commutator. Brushes ride against the commutator segments while the motor is running. Brush lifting rotor uses a radial commutator. Weights mounted at the front of the armature. Okay. Repulsion induction motors continued like repulsion motor, but with squirrel cage windings on armature. No centrifugal mechanism or short-circuiting device. These have a high starting torque due to starting as a repulsion motor, but better speed characteristics due to the squirrel cage. All right, everybody get a look at that. Stepping motors convert electrical impulses into mechanical movement. An output shaft moves through specific angular rotation each time the motor receives a pulse, allowing control of speed, distance, or position. The theory of their operation is they operate on the principle of magnetic attraction and repulsion. They must have 8 stator poles and teeth machined in pole pieces and rotor. Stepping motors continue. Windings, different winding methods. Standard 3-lead motor or bifiller. 4-step switching or full stepping takes 4 steps, changes of switch position for the rotor to advance 1 tooth. 8-step switching or half stepping. Rotor advances 1/8 of a tooth per step instead of 1/4 for better speed capability. AC operation. Stepping motor operates on AC voltage, becomes 2-phase, synchronous, constant speed motor. Permanent magnet induction motor. No brushes, slip rings, commutators, gears, or belts. Stepping motor characteristics. Used as 2-phase synchronous motors. Stop, start, reverse direction nearly instantly. Maintain stalled condition without harm. No high inrush current. Starting and running current are the same. Okay. Universal motors, also called AC series motor, has wound armature and brushes like DC series motor, but adds a compensating winding and other improvements for handling AC. These motors operate on DC or AC. The compensating winding for AC, the conductive compensation is in series with the armature, and inductive compensation is achieved by shorting the leads together, but cannot be used with DC. Universal motors continued. The neutral plane. Set brushes in the neutral plane using either series or compensating winding. Speed regulation is very poor. Speed almost unlimited at light or no load. Produces high horsepower for size and weight. Changing the direction of the rotation of a universal motor. Changing the armature leads with respect to the field leads. So pretty much the same thing as a DC motor there on the universal. You just have to change one of the directions of the rotating magnetic field. Okay, good. We're at the summary. All single-phase motors operate on the principle of a rotating magnetic field. Split-phase motors start as 2-phase motors, produce an out-of-phase condition for current in the start and run windings. Maximum starting torque for split-phase motor develops when a start winding current and run winding current are 90 degrees out of phase with each other. Capacitor run motor operates as a 2-phase motor. Shaded pole induction motor rotating magnetic field is produced by placing a shaded coil on one side of the pole piece. Consequent pole motors change motor speed and maintain a high torque. Multi-speed motors connect windings in series with the main run winding. 3 basic types of repulsion motors are repulsion motor, repulsion start induction run, and repulsion induction motor. 2 types of single-phase motors are Warren and Holtz. Stepping motors produce angular movements in steps. Universal motors operate on DC or AC and contain wound armatures and brushes. Okay, now we have gone through the slides that the book had assigned to you. Now it's time to supplement them with something awesome. Let me get down here to the bare bones of where I want to go. Dismiss. 226, where did it go? Was up here. 226. Shaded pole. Okay, we're just going to hit this real quick. 20 slides. Hopefully we can get through this today, but hopefully this will give us a little bit better idea of what's up. From beginning. All right. Shaded pole induction motors. Shaded pole induction motors are small single-phase motors that do not require start winding, centrifugal switch, or starting capacitors. They are generally small in size and used in low-power applications like fans and blowers. Induction-type motors contain squirrel cage rotors similar to those found in other types of induction motors. Okay, shaded pole motors are so named because one side of each pole is surrounded by a large copper conductor called a shading coil.
Right here is the shading coil. And once you use the left-hand motors, you can see, you actually see that it's pretty obvious.
To understand how a shaded pole induction motor operates, first review some of the basic rules concerning magnetism and magnetic induction. Man, I bet you guys thought that stuff was going away. It's not. It's here to stay. Anytime current flows through a conductor, a magnetic field is created around the conductor. When a conductor is cut by a magnetic field, a voltage is induced into the conductor. The strength of the electromagnetic field is proportional to the rate of change of current. Okay, now this is actually what I wanted to see. And this gives us a little bit broader view of what's happening inside of these in the book's slides. So when current first starts to increase in the coil, the rate of change of the current is high, producing a strong, rapidly changing magnetic field. This changing magnetic field induces a voltage into the shading coil. All right, everybody see that there? How those lines of flux are starting to condense themselves right there? Since the shading coil is a shorted loop, the induced voltage causes a current to flow in the shaded coil. The current flow in the shaded coil produces a separate magnetic field that is opposed to the magnetic field producing it. Okay? Opposition to a rotating magnetic field. That's how we're doing this motor stuff. The magnetic field of the shading coil causes the magnetic field of the pole piece to deflect and concentrate in one part of the pole piece. So you see how it's all concentrating right there? It's causing that deflection of the lines of flux to concentrate right there. Heck yeah, you see that? As the current approaches its maximum value, so as we reach almost to the top of that sine wave, the rate of change is less, causing less induced voltage into the shaded coil. This reduces the magnetic field opposing the magnetic field of the pole piece, allowing the magnetic lines of flux to enter the shaded area of the pole piece. So now we don't have it so concentrated over here, because we've gone through that initial stage in the sine wave, and now that we're getting up here to where the rate change is slow, we are allowing the magnetic lines of flux to now enter into the shading coil area. Okay? When the current reaches its maximum value, there is no longer any change. Okay, so we can't do anything. We're as changed as much as we can go as far as moving up the system is gone, moving up the wave. All right, since the current is not changing in value, there is no induced current into the shading coil and no magnetic field to oppose it. The magnetic field of the pole piece. The magnetic lines of flux are now uniform across the face of the pole piece. Okay, we're at the peak of this wave.
Now, just observe what happens when we go back down, okay? At this point in the sine wave, we're on a single pole motor, we have the north and the south, it's being cut by the rotor, okay?
As the current decreases from its maximum value, it is again changing. The current change again induces a voltage into the shading coil, causing the current to flow in the opposite direction. The magnetic field produced by the shading coil now aids the pole piece in the production of magnetism, causing the magnetism to become more concentrated in that area of the pole. Now you guys can observe as we start to
Decline back down the wave, our concentration on the magnetic field is now more heavily concentrated on this side, and the shading coil's current flow is pointing in the opposite direction that it was. Okay?
As the current approaches zero, the rate of change is greater, causing more induced voltage and current at the shading coil. The increased current causes the magnetic field of the shading coil to become stronger and attract more magnetic lines of force produced by the pole piece. The magnetic field of the pole piece is now concentrated in the shaded area of the pole. So man, we just dominated that whole magnetic field now, and we're running it through the shading coil. What do we got here? When viewed in real time, there we go. When viewed in real time, the magnetic field will rotate around the stator poles. The speed of the rotating magnetic field is called the synchronous speed and is proportional to the number of stator poles and the frequency of the applied voltage.
So this is what I was talking about how we actually have some neat graphics that will actually show us what's happening. So inside of here, as our sine wave, say for instance we have a wire coming off of here, and these are all tied together, and we have another wire coming off of there, and the wire goes up. This is how the interior rotating magnetic field is going to look if we apply our voltage to this, our single wave voltage. Okay? And that reaction of this rotating magnetic field here and how it reacts to the inside rotor, the induced voltage is going to, so as this is rotating, it appears to be rotating like this. But now as it is inducing the voltage, we have conductors, which are a squirrel cage inside the rotor. As that magnetic field is coming those conductors, the opposition to this rotation is going to cause the rotor to rotate like this. Okay? Everybody see that?
That opposition to that rotating magnetic field is going to be induced into the rotor, and that opposition is what makes that stuff start to rotate. Hopefully, oh, bam, there we go. Going a lot faster on mine. The rotating magnetic field induces a current into the bars of the squirrel cage. So each one of these guys right here is magnetic conductors. Okay, so remember that we talked about magnetic induction at the beginning of this one, and about how it's never going to go away, because here it is again. Okay, there is no electrical conductivity between the rotor and the stator in these. Unlike DC motor, where we do have electrical conductivity with the brushes. Okay, all of this is happening because of induction. Ain't that cool? I think so. Hell yeah, I think that's super cool. All right. The rotor current produces a magnetic field around the rotor, which is attracted to the rotating field of the of the stator. The rotor turns in the same direction as the rotating magnetic field. Okay, well, that's a little different than I said, but it's got to be right, right? All right, shaded pole motors are very limited in the amount of torque or turning force that they can produce. These motors are generally employed to operate such devices as small fans and blowers. Yes, sir. Yes, sir. Other types of shaded pole. Many types of small shaded pole motors contain two poles. These motors are used to operate very small fans or other low torque loads. These motors have a synchronous speed of 3,600 RPM when operated at 60 Hertz. Synchronous speed is the speed of the rotating magnetic field. All right. I love the graphics on these. They really kind of just drive it home what's actually happening. Another common type of shaded pole motor is the single-phase sync motor. These two basic types are the Warren and the Holtz. These two motors differ in the construction of the rotor. The Warren motor shown here has a motor that produces a low reluctance path through the rotor. The low reluctance path permits the rotor to lock in step where the rotating magnetic field. The Warren motor will operate at 3,600 RPM. The Holtz motor has 6 salient projecting poles.
Okay, this is the salient projecting pole right here. Okay. Bars on the squirrel cage type winding are located at the bottom of the pole slots. 6 salient poles per minute motor, 2 turn at a constant speed of 1,200 RPM when the motor is hooked up to 60 hertz. Small sync type shaded pole motors develop very little torque
And are generally employed to operate devices that must operate at a constant speed, such as clocks, timers, and were often used to operate phonograph or record players. We should ask Scott about that, huh? Scott or Bill? Remember when you used to have to wind those things up, guys? What was that about? End of that. Okay. Well, I got 10 minutes left, and I intend on using it. So, any questions on shaded pole motors? The reality of them is they're so simple. You don't really have to work on them. You can take them apart and look at the different parts, and we can probably do that in our lab. That might be fun just to see what one looks like apart. I'll go grab one. But unless there's not any questions, we're going to get off of this and move into split phase part 1. Okay. This is where we're going to maybe slow down a little bit and actually drill into what this guy's talking about. So we'll get started with it today. Slideshow from the beginning. All right. Split phase motors, part 1. Split phase motors are single phase motors that operate on 120 or 240 volts. There are 3 basic types of motors. Induction run, capacitor start induction run, capacitor start capacitor run, or PSC, permanent split capacitor. Okay, when we're talking single phase motors,
this is what you're going to be dealing with when you hit the streets. Okay, guys, you're not going to see any of the stuff that we really talked about at the end there. I've spent years in the field and never seen a universal motor, and I've never seen a brushed AC motor. So these are really ultimately what we're going to be dealing with right here. Split phase motors start by producing a rotating magnetic field inside of the stator winding. They receive their name from the manner in which the rotating field is produced. A rotating magnetic field cannot be produced with a single phase. Split phase motors split in a single phase and make a second phase, much like two-phase power system. Okay, graphics, I love them. I love these. I wish we had these around. Two-phase power is produced by placing 2 separate windings at a 90-degree angle. When the magnetic field cuts the windings, 2 separate voltages 90 degrees out of phase with each other are produced. A rotating magnetic field can be produced by two-phase power. So when we're doing two-phase power, it's going to be off by 90 degrees. How many degrees off are three-phase power? Not much. 220. 120. Very good. Thank you for having it. I'm going to start talking about three-phase after we get done with this. And then all that stuff's going to start making sense.
All right. I love the graphic. Okay, here's what we were talking about earlier.
You get the lights on here just so we can see what's going on. Okay. Split phase motors contain two windings.
A run winding and a start winding. The start winding of the resistance start induction run and capacitor start induction run motors is made with a much smaller wire and placed closer to the top of the iron core of the stator than the run winding. So remember that. That might be something worth having knowledge on when we hit test time. Okay. The run winding is made up with larger wire and placed at the bottom of the iron core of the stator. The stator windings are placed at a 90-degree angle in reference to the run winding. Okay, does everybody see that?
Can you see the difference? The translation on this line is a little different because of the, but I can see, I don't know that you can. These guys are different sizes. This seems to be smaller than medium in this guy. Okay? And I can't really tell whether it's sticking to the iron core here. You know, I can subtract the volume. So they must be. Now, it's really tough to see that on this picture, but at least it
Can show you a little bit of a difference between the size. And if you guys want a more clear illustration of that, you're welcome to. I'll probably put these on there like I did the other ones just so you can see. But for the most part, you should be able to kind of see that. Okay. Run and start windings are connected in parallel with each other. Since these windings are connected in parallel, both receive the same voltage from the power source. Electrically, the start and run windings exhibit different characteristics. The run winding is made with larger wire and placed deeper in the core. The larger wiring has less resistance than the small wire of the starting winding. The small wire of the start winding contains more resistance than the run winding. Placing the start winding closer to the top of the iron stator core causes it to exhibit less inductance than the run winding. Therefore, the run winding has less resistance and more inductance than the start winding, and the start winding has more inductance, more resistance and less inductance than the run winding. Geez, I thought my laser was pointing at you guys back there. All right. So this will probably be the last one that I'm going to do today. The resistance start induction run motors. Since the start winding contains more resistance and less inductance than the run windings, the current flow through the through the start winding will be less out of phase with the voltage than the current flow through the run winding. The run winding contains more inductance and less resistance than the start winding, causing the current flow through the run winding to be more out of phase with the voltage than the current flow through the start windings. The resistance start induction run motor develops a phase angle difference of about 35 to 40 degrees between the run winding current and the start winding current. So did everybody understand that?
So because of how much long leads in there, the start winding current and the run winding current are going to be what generate that difference in the phase. They have a phase current, and that difference is what can start that rotational magnetic field. Okay? And where do we get that? Silence is yes. What else? Let's see if we can see one picture.
Not moving. It is on mine. It's moving too fast. There it goes. That's what it's trying to tell you. And that's what we'll pick up. Right. Okay. Any questions? Okay, remember that if you didn't turn your work in the day before class, you can still do it till Friday after 5 to 0. Okay. Everybody else take a little break. See you back here.
Granted,